Venus should have been one of the most Earth-like planets in the solar system. Almost the same size, almost the same mass, made of the same rocky material, and yet it turned into the hottest planet in our neighbourhood, buried under crushing pressure and clouds of acid. So what went wrong? Did Venus once have oceans, a milder climate, maybe even conditions that could have supported life before everything collapsed? In this video, you're going to see how a planet that may have started with many of the same ingredients as Earth became a world of permanent heat, lost water, and atmospheric disaster. And why that makes Venus one of the most important warning signs in planetary science. But before we continue, please subscribe to the channel to give your support. Let's continue. So how similar are Venus and Earth, really? A lot. Venus has a diameter of about 12,104 kilometers, or 7,521 miles. Earth is about 12,742 kilometers, or 7,918 miles across. Venus has about 81.5% of Earth's mass. Its surface gravity is about 8.87 meters per second squared, or about 0.9 g. That means if you weigh 180 pounds on Earth, you would weigh about 162 pounds on Venus. So in terms of size, weight, density, and overall rocky structure, Venus is not some weird outlier. It is the closest thing we have to a sister planet in our own solar system. And that immediately gives you the real problem. If Venus and Earth are so close in the basic things that usually matter, size, mass, density, rocky composition, then why did one world become oceans, weather, and life while the other became a furnace? That is not a small difference. That is a total break in planetary history. And once you see that, Venus stops looking like just another planet. It becomes a case study in how badly a world can go wrong. So did they also begin in similar ways? Most likely yes. Both Venus and Earth formed around 4.5 billion years ago from rocky material in the inner solar system. Both probably started out hot, violent, and unstable. Both were hit by asteroids during the early bombardment era. Both likely had intense volcanism. Both likely released huge amounts of gases from their interiors, things like carbon dioxide, water vapour, nitrogen, and sulfur-bearing gases. In plain language, both planets probably began with the same kind of basic planetary ingredients. Hot rock, active geology, thick early atmospheres, and a lot of chemistry happening fast. That is important, because it means Venus may once have had a real chance to become more temperate. Not guaranteed, not proven, but possible. It had rock, heat, atmosphere, volcanic outgassing, and maybe water. So the mystery is not whether Venus had the raw materials for an Earth-like world. It probably did. The mystery is why those raw materials did not stay in balance. Why did Earth stabilize while Venus did not? Why did one planet hold on to conditions that could support liquid water, while the other ended up completely hostile? Now here is where the story turns. The biggest early difference between the two planets may have been one simple thing: location. Venus orbits the Sun at about 0.72 astronomical units. Earth is at 1 astronomical unit. That means Venus gets much more solar energy, about 1.9 times as much as Earth. And that difference may sound manageable at first, but planetary climate does not always respond in a smooth way. A system can handle extra heat for a while, then reach a threshold where the response becomes extreme. That is the key point. Climate systems are non-linear. A planet can warm a little and stay stable, but if it warms too much, the feedbacks start reinforcing each other. More heat causes more evaporation. More water vapour in the atmosphere causes stronger greenhouse trapping. Stronger greenhouse trapping causes more heat, and once that cycle starts running hard enough, it gets much harder for the planet to cool itself again. So Venus may not have needed some rare cosmic accident. It may simply have been close enough to the Sun that over geologic time, stability became harder and harder to maintain. But here is the part that makes Venus so important. This is not just about one unlucky planet. Venus changes how scientists think about habitability itself. People often hear terms like Earth-sized or rocky planet and assume that means a world is probably safe, maybe even livable. Venus shows that is not enough. A planet can be almost the same size as Earth, made of similar material, formed in the same solar system, and still become catastrophic. That matters for understanding Earth's own history, it matters for climate science, and it matters for exoplanets. Because a distant rocky planet in the right size range might still be much closer to Venus than to Earth. So Venus is not just a dead planet sitting next to us, it is one of the clearest warnings in planetary science. It tells scientists that habitability may not be a permanent condition. It may be a phase, something a planet can gain, keep for a while, and then lose. Venus helps define the inner edge of the habitable zone, the region around a star where liquid water might be possible. It helps scientists test how greenhouse feedbacks work at the extreme limit. And it raises a bigger question that sits underneath this whole story. Is a habitable world naturally stable? Or is it always at risk of tipping into something much worse? And that leads directly to the main question behind this entire video. Was Venus once like Earth? That sounds simple, but it breaks into several harder questions. Did Venus ever have oceans? If it did, were they there briefly, or for billions of years? Was the climate ever mild and stable? Did volcanism slowly poison the atmosphere? Did the sun gradually push Venus over a limit? Did Venus fail because it could not recycle carbon the way Earth does? Or did it lose control very early and never recover? Those are the questions that drive the whole investigation. Because if Venus once had conditions even somewhat like Earth, then what we are looking at today is the end result of a planetary collapse. And if that is true, then the next question becomes the most important one in the story. If Venus really was once more Earth-like, then where is the evidence? The first place scientists look is the most obvious one. And the most important one. Water. The next question is simple, and it decides almost everything. Did Venus ever actually have water on the surface? Because when scientists ask whether Venus was once like Earth, that is really what they are testing. Not whether it was rocky, not whether it had an atmosphere, not whether it formed in the same part of the solar system. The first real test is liquid water. If Venus once had stable water on the surface, then the idea of an ancient Earth like Venus becomes much more serious. If it never did, then the whole picture changes. And water matters for more than just life. People hear water and immediately think biology. But for a planet, water does much more than that. Water helps control temperature. It stores heat, moves heat, dissolves gases, changes rocks, drives erosion, and helps run long-term climate chemistry. Oceans can pull carbon dioxide out of the air, interact with the crust, and slow down climate swings. So when scientists talk about a planet being Earth-like, they do not just mean a planet with the right size and gravity. They usually mean a planet where liquid water can exist for long periods and shape the whole environment. Without that, a world can still be fascinating, but it is much harder to call it Earth-like in the normal sense. So what is the evidence? One of the biggest clues is hidden in a very small detail, a strange fingerprint in the atmosphere. Scientists look at something called the deuterium to hydrogen ratio, usually shortened to D/H. That sounds technical, but the basic idea is simple. Hydrogen comes in a lighter normal version and a heavier version called deuterium. Water can contain either one. If a planet loses water over time, and that water gets broken apart, the lighter hydrogen escapes to space more easily than the heavier deuterium. So as more and more hydrogen is lost, the water left behind becomes richer in deuterium. And that is exactly what Venus shows. Its atmosphere has a deuterium to hydrogen ratio far higher than Earth's, commonly described as around 150 times the value found in Earth's oceans. That does not tell scientists the exact size of ancient Venusian oceans, and it does not work like a perfect measuring cup. But it is one of the strongest signs we have that Venus lost a huge amount of hydrogen in the past, and that strongly points to major water loss. In plain language, Venus looks like a planet that used to be much wetter than it is now. Now here is the important question. Does that mean Venus definitely had oceans? Not necessarily, and this is where the story gets more difficult. The evidence supports major water loss, but it does not prove exactly what that water looked like on the surface. It could have been shallow seas. It could have been long-lived lakes. It could have been a much wetter atmosphere over a long period. It could even mean Venus had a lot of water early on, but lost it before stable oceans fully settled in the way people picture them. So the honest answer is that scientists do not yet know whether ancient Venus had blue oceans and coastlines in the cinematic sense. But they also cannot rule it out. Some climate models suggest Venus could have had shallow oceans, or at least long-lasting liquid water at the surface, especially if thick clouds reflected enough sunlight back to space to keep the planet cooler. One influential NASA modeling study found that under some conditions, Venus-like planets could maintain habitable temperatures for nearly 3 billion years. That is a huge claim, and it does not mean the case is closed. It depends on assumptions about early atmosphere, cloud behavior, rotation, and topography. Other studies argue almost the opposite, that Venus may have become dry much earlier, maybe after a very hot magma ocean phase that caused water to be lost fast. So the scientific picture is not settled. That uncertainty is important, because it means Venus is not just a solved story where scientists already know the ending in detail. The big issue is timing. Did Venus stay temperate for a very long time, then collapse later? Or did it lose water so early that it never really had a stable Earth-like phase at all? Those are very different histories. One version gives you a planet that may have stayed habitable for ages before failing. The other gives you a planet that was always close to disaster and crossed the line early. And if you want to understand how extreme the difference is, look at Venus today. The modern planet is incredibly dry. The lower atmosphere has only trace amounts of water vapor. The total amount of water still present is tiny compared with Earth. In many standard discussions of runaway greenhouse collapse, the remaining water inventory on Venus is estimated at around 100,000th of Earth's ocean inventory. That is not less water than Earth. That is almost no water at all on planetary terms. So whatever Venus once had, it is almost entirely gone now. That is why modern Venus is not just hot. It is desiccated. The water story has almost completely ended there. On Earth, water cycles through oceans, clouds, rivers, ice, soil, and atmosphere. On Venus, that cycle is basically gone. There is no active hydrological system shaping the surface the way it does on Earth. No rainfall carving landscapes, no oceans buffering climate, no large surface reservoirs moving heat around the planet. If Venus once had a world shaped by water, that world has been erased so thoroughly that only atmospheric clues remain. So what are scientists still trying to figure out? The biggest unknown is not whether Venus is dry now. That part is obvious. The hardest question is when the drying happened, and how fast. Did Venus lose its water quickly, early, and violently, maybe during the first stages of its history? Or did it keep water for hundreds of millions, maybe even billions of years, before climate feedbacks finally pushed it past the point of no return? That difference changes everything. If Venus stayed wet for a long time, then planets closer to their stars might remain habitable longer than scientists once thought. That would expand the range of worlds that might support life, at least for a while. But if Venus dried out very early, then Earth-like conditions may be easier to lose than we assumed, especially during the chaotic, early stages of planetary evolution. In other words, Venus is not only telling us about Venus, it is helping scientists test how fragile habitability really is. And this is exactly why future missions are so focused on atmospheric chemistry, noble gases, and surface composition. The atmosphere may still hold the record of what happened to the water. Ratios of gases, traces of escape processes, and chemical clues in the lower atmosphere may help scientists work out whether Venus lost its water in one major transition or through a slower long decline. Surface minerals may also help if future missions can measure them clearly enough. The planet may still preserve the evidence, but right now the evidence is incomplete. So the most direct answer for this section is this. Yes, Venus shows strong signs that it lost a lot of water. No, scientists still cannot say with confidence exactly how much surface water it once had, or how long it lasted. That is why Venus is so compelling. It is not just a hot planet. It may be a world that once had one of the most important ingredients for an Earth-like environment, then lost almost all of it. And once you accept that, the tension gets even worse. Because the next question is no longer whether Venus had water. The next question is what destroyed it. What kind of planetary process can take a world with major water loss in its past and turn it into the hottest surface of any planet in the solar system? That is where the story moves from possibility to mechanism. And that mechanism is the runaway greenhouse. Venus did not become a furnace just because it was a little closer to the sun. It became a furnace because its climate crossed a line and then kept moving in the wrong direction. That is the key idea in this whole section. A lot of people hear the phrase greenhouse effect and think it automatically means disaster, but that is not true. Earth has a greenhouse effect too, and without it, this planet would be far colder and much harder for life to survive on. A greenhouse effect is just what happens when gases in an atmosphere trap some of the outgoing heat trying to escape into space. The problem starts when that heat trapping becomes too strong, because then the planet cannot cool itself efficiently anymore. And Venus is the most extreme example of that in the inner solar system. Its atmosphere is about 96.5% carbon dioxide. The pressure at the surface is about 92 times higher than the pressure at sea level on Earth. A simple way to understand that is to think of the pressure you would feel deep under the ocean, around 900 meters down, or close to 3,000 feet. Except on Venus, that pressure is not underwater. It is just standing on the ground. And the heat is even worse. The average surface temperature is around 735 Kelvin, which is about 462 degrees Celsius, or 864 degrees Fahrenheit. That is hot enough to melt lead. So when scientists say Venus has a runaway greenhouse, they are not talking about a slightly overheated world. They are talking about a planet where the atmosphere has taken control of the entire surface environment. So how does a planet get pushed that far? The basic mechanism is simple, and that is part of what makes it so unsettling. As a planet warms up, more water evaporates. That sounds normal, but water vapor is also a greenhouse gas. So now the warmer atmosphere traps more heat. That extra heat causes even more water to evaporate. Then even more heat gets trapped. Then more evaporation happens again. This is a feedback loop. And as long as the loop keeps strengthening, the climate does not just shift, it starts amplifying itself. That is the tipping point people mean when they talk about a runaway greenhouse. At first, a planet may still have oceans, clouds, rainfall, and other systems that help distribute heat and stabilize the climate. But if warming gets strong enough, those oceans become harder to maintain. More of the water moves into the atmosphere as vapor. The upper atmosphere becomes wetter. And once water reaches high enough altitudes, sunlight can break those water molecules apart. The hydrogen escapes into space much more easily, and once that hydrogen is gone, the planet cannot easily rebuild its water. The oxygen that remains does not just sit there neatly waiting to form oceans again. It can react with rocks, get absorbed into the crust, or be lost through other processes. So now the planet has lost something essential. It has lost one of the main systems that could regulate its own climate. Oceans do not just store water, they store heat, support weathering, dissolve gases, and help remove carbon dioxide from the atmosphere over long timescales. Once a planet loses stable surface water, it loses a huge part of its ability to resist further warming. That is why the phrase runaway greenhouse matters so much. The disaster is not just that the planet heats up. The disaster is that the planet destroys one of the main tools it had to stop the heating. And that leads to the next problem. Because even after water is lost, the atmosphere does not stop evolving. On Earth, there are long-term systems that help regulate carbon dioxide. Oceans absorb it. Rain and rock weathering help lock it away. Plate tectonics helps cycle carbon into the crust and mantle and back out again over millions of years. It is not a perfect system, but it works as a deep-time climate regulator. Venus appears to lack anything like Earth's plate tectonics today, or at least anything equally effective at global carbon recycling. That difference matters a lot, because if a planet has active volcanism releasing carbon dioxide, but weak long-term systems for removing that carbon dioxide, then the atmosphere can keep getting thicker and hotter. And once Venus lost its water, it may also have lost the chemistry and weathering processes that could have helped slow that build-up down. So the planet may have reached a stage where the climate system no longer had a realistic path back to stability. Not because one single thing went wrong, but because multiple stabilizers failed, one after another. Water was lost, carbon removal weakened, greenhouse gases accumulated, and the surface kept heating. Now here is another reason Venus is so extreme. Its modern atmosphere is not just rich in greenhouse gases, it is enormous. It is so deep and dense that it spreads heat around the planet very efficiently. That means Venus is not only scorching on the day side and cooler on the night side. Near the surface, the temperatures stay brutally high, almost everywhere. The whole lower atmosphere acts like a global heat reservoir. Heat does not escape easily, and it does not stay isolated in one region for long. This becomes even stranger when you remember how slowly Venus rotates. Venus turns so slowly that one sidereal day on Venus is longer than one Venus year. In other words, the planet rotates so slowly on its axis that you might expect huge differences between the side facing the Sun and the side facing away from it. But that is not what dominates near the surface. High above the planet, the atmosphere moves much faster than the solid world below it. This is called superrotation. Winds in the upper atmosphere race around the planet in just a few days, so even though the ground turns slowly, the atmosphere is dynamic, fast-moving, and very good at redistributing heat. That is why Venus is not just hot in sunlight. It is hot as a system. The atmosphere has become the main climate machine. Once a planet reaches that stage, day and night matter less than you would think, because the atmosphere is now doing the real work of holding and moving energy. It is a fully established heat trap on a global scale, and this is the most important way to frame the story. Venus did not simply warm up more than Earth, it crossed a threshold. That is the real difference. Earth-like climate systems can take shocks, adjust, and settle into new balances. Venus seems to have lost that ability. At some point, the normal balancing forces were no longer enough. The warming did not level off in time. The water cycle broke down. The major long-term cooling mechanisms weakened. The atmosphere thickened. And once the oceans were gone, the greenhouse state became much harder, maybe impossible, to reverse. So when you look at Venus today, you are not looking at a planet that is just hotter than Earth. You are looking at a planet where the climate system itself changed category. It became a world locked into permanent global overheating. And that is what makes Venus so important, because it shows that climate collapse on a planet is not just about temperature going up. It is about the whole system losing the ability to pull itself back. And once that happens, the next question gets even worse. Because if the greenhouse effect turned Venus into a global furnace, then what exactly is this atmosphere made of now? How deep is it? How toxic is it? And why does it keep the surface this deadly all the time? That is where the story moves from the mechanism of collapse to the environment that collapse created, the atmosphere of Venus itself. How extreme does an atmosphere have to be before the atmosphere itself becomes the planet's main surface environment? On Venus, that is exactly what happened. The air is not just something above the ground. It is the main reason the ground is so deadly. If you could somehow stand on Venus, the first thing trying to kill you would not be one single factor. It would be everything at once: the heat, the pressure, the chemistry, and the fact that the atmosphere is so massive that it controls almost the entire planet near the surface. Start with the basic makeup. Venus's atmosphere is mostly carbon dioxide. Nitrogen makes up much of the rest. And then there are trace amounts of water vapour, sulfur-bearing gases, and a few other components mixed in. That matters because carbon dioxide is very good at trapping infrared heat, the kind of heat a planet tries to radiate back into space after it absorbs sunlight. So right away, Venus has one of the strongest possible setups for a greenhouse effect. But there is an important point here. It is not just that Venus has carbon dioxide. It is that Venus has an enormous amount of it. That is the part people often miss. Composition matters, but mass matters too. Venus does not just have a greenhouse gas in the air. It has a deep global envelope of atmosphere, so thick and heavy that near the surface it behaves almost like an ocean of gas. And once you have that much atmosphere sitting on top of a planet, you get a system that traps heat efficiently, spreads heat efficiently, and makes the entire lower environment much more stable in the worst possible way. Stable not in the sense of safe, but in the sense that the planet stays brutally hot all the time. So how dense is this air really? The pressure at the surface of Venus is about 9.2 megapascals, or about 92 bar. That means it is around 92 times the air pressure at sea level on Earth. A normal human comparison is deep ocean pressure, roughly what you would experience around 900 meters down, or close to 3,000 feet below sea level. Except on Venus, again, that is just the surface. You are not diving into water, you are just standing there. And the atmosphere itself is pressing down on you with that kind of force. That is why landing on Venus is such a hard engineering problem. A spacecraft does not just have to survive high heat, it has to survive being crushed while being baked. Electronics fail faster in that kind of heat. Mechanical systems are under huge stress. Materials expand, weaken, and break down. Seals and joints become failure points. Every part of the lander is under attack at the same time. That is why the Soviet Venera landers, despite being some of the toughest spacecraft ever sent to another planet, only survived briefly on the surface before the environment destroyed them. Venus is hostile in a full system way. It does not challenge one part of your machine. It challenges all of it at once. Now here is the next twist, because if you look at Venus in the sky, it does not look like a world that should be this bad. Venus is bright, smooth, white, and covered in cloud. To a casual observer, it can seem calm, even beautiful. But those clouds are not made of water like Earth's clouds. They are made largely of sulfuric acid droplets. So the bright reflective blanket you see from far away is not a sign of a mild atmosphere. It is part of a chemically aggressive one, and those sulfuric acid clouds create one of the strangest contrasts on Venus. They reflect a lot of sunlight back into space, which is one reason Venus appears so bright from Earth. In other words, the cloud tops are actually helping reduce how much solar energy gets deeper into the atmosphere. But below that reflective cloud layer, the lower atmosphere is still unbelievably hot. So Venus is a planet where part of the atmosphere is blocking sunlight, while another part is still trapping heat so efficiently that the surface remains hot enough to melt lead. That is why Venus can confuse people at first. Bright clouds sound cool, high reflectivity sounds like protection. But on Venus, that is only part of the story. The greenhouse system below is so powerful that even with very reflective clouds, the surface remains catastrophic. So is the atmosphere at least calm once you get past the clouds? Not at all. Venus's atmosphere is active, fast-moving, and still not fully understood. High above the surface, winds can circle the planet in just a few days. That is called superrotation. The atmosphere moves vastly faster than the solid planet below it. And that is especially strange because Venus itself rotates extremely slowly. The planet turns so slowly that you might expect everything about its climate to move slowly too. But the atmosphere does not follow that logic. It races around the planet, carrying heat, chemicals and momentum with it. Scientists are still working out exactly how this superrotation is maintained so strongly. But the big point for the story is clear. Venus's atmosphere is not static. It is not just a thick blanket sitting there doing nothing. It is a dynamic machine. It redistributes energy. It drives complex circulation. It supports large cloud systems. It moves sulfur chemistry around the planet. And it helps make Venus a world where the atmosphere is doing much more than simply existing above the ground. It is constantly shaping the entire climate system. That leads to one of the most important differences between Venus and Earth. On Earth, when you think about weather, you are mostly thinking about water. Clouds, rain, in snow, rivers, storms, evaporation, humidity. Water is central to how Earth's atmosphere behaves. On Venus, weather is much more about sulfur chemistry, cloud droplets made of acid, radiative transfer, and circulation inside a carbon dioxide-heavy atmosphere. That is a completely different regime. The rules are not the same. The familiar Earth pattern of water cycling between ocean, sky, and land is basically gone. So Venus does not simply have worse weather than Earth. It has a different kind of atmospheric world altogether. It is a place where the climate system has diverged so far from Earth's that ordinary comparisons start to break down. The air is denser, hotter, more chemically aggressive, and more dominant over the surface. The clouds are not made of water. The circulation is extreme. The greenhouse trapping is locked in. And the result is a planet where the atmosphere is not just part of the story, it is the story. And once you understand that, the next question gets even sharper, because if the atmosphere is this extreme, then what does the ground beneath it actually look like? What kind of world sits under all that pressure, acid cloud, and permanent heat? Is it ancient and dead? Or is it still changing? Because the answer turns out to make Venus even more active and even more disturbing than people once thought. If the atmosphere of Venus is this extreme, then what kind of ground is hiding underneath it? For a long time, that was a real mystery, because Venus is covered by thick clouds that block normal visible light views of the surface. You cannot just point a regular camera at Venus from orbit and see continents, craters, or volcanoes the way you can on Mars or the Moon. That meant scientists had to use radar to see through the clouds and map what was actually down there. And when they finally did, the result was not a boring rock ball. It was a planet with a huge amount of geological activity written all over it. The mission that changed everything was NASA's Magellan spacecraft in the 1990s. Magellan used radar to map almost the entire surface of Venus in detail. And what it revealed was a world covered in enormous volcanic plains, twisted highlands, rift zones, giant shield volcanoes, strange circular structures called coronae, and thick rounded lava features known as pancake domes. So Venus was not hiding a simple dead landscape under those clouds. It was hiding one of the most dramatic rocky surfaces in the solar system. That matters because the surface tells you what kind of internal life a planet still has, or had not that long ago. If Venus had just cooled down early and stayed geologically dead, then maybe its climate story would be simpler. But that is not what the radar maps showed. The surface looks like it has been shaped again and again by internal forces, especially volcanism and tectonic deformation. In other words, Venus is not just a planet with a bad atmosphere. It is a planet whose interior seems to have stayed active enough to keep rewriting the crust. Now here is the next important clue. Venus has a surprisingly low number of impact craters compared with what you might expect from an old rocky world. That is a big deal, because impact craters are one of the main ways scientists estimate how old a planetary surface is. On a surface that has been sitting unchanged for billions of years, craters pile up. On a surface that has been renewed, buried, or reshaped, many of those old craters disappear. And Venus looks more like the second case. Much of the visible surface seems geologically young on planetary timescales. A long-standing estimate places major resurfacing on Venus somewhere around 300 to 500 million years ago. That does not mean every part of the planet changed all at once in one perfectly clean event. The exact timing and style are still debated. Some scientists argue for something like widespread, catastrophic resurfacing, where huge amounts of volcanic and tectonic activity renewed much of the planet over a relatively short span. Others argue for a more distributed, long-duration process where resurfacing happened in many places over extended periods. But either way, the message is the same. Venus did not just cool off and freeze into place. Something big happened there, and it erased a lot of older surface history. That makes the planet much more interesting and much more difficult to decode. If the surface has been renewed, then some of the evidence of very ancient Venus may be gone, buried under lava flows or reworked by tectonic processes. So the rocks are giving scientists clues, but they are also hiding part of the story. It is like trying to reconstruct someone's life from a document that has been partially burned and rewritten. And now the tension gets even higher. Because Venus may not just have been volcanic in the distant past, it may still be volcanically active now. Recent reanalysis of Magellan radar data found strong evidence that at least one volcanic vent changed shape during the mission, consistent with an eruption in the early 1990s. That result was especially tied to Mont Mons, one of the major volcanoes on Venus. Later studies pointed to signs of additional eruptions at other sites too. So the picture is shifting. Venus is not just a world that used to erupt. It may be a world that is still erupting. That is a huge point for this story. If Venus still has active volcanism, then the surface and atmosphere are still connected in a live system. Volcanoes can release gases into the atmosphere, including carbon dioxide and sulfur-bearing gases. That means active volcanism could still be feeding the chemistry of the atmosphere today. It could help explain why Venus remains so dynamic instead of being just an old static ruin. And it also means the climate disaster on Venus may not only be an ancient event. The planet's interior may still be helping maintain the conditions we see now. So what does geology look like on a planet with no oceans, no rivers, and no rainfall at the surface? Very different from Earth. On Earth, water does a huge amount of geological work. Rivers cut valleys, rain erodes mountains, sediment gets carried into lakes and oceans, coastlines shift. Water shapes the surface constantly. Venus does not have that kind of surface water system. So its geology speaks in a different way. Lava flows matter more. Crustal deformation matters more. Gravity-driven collapse matters more. Chemical weathering in the thick atmosphere matters more. That is why Venus is such a useful reminder that a rocky planet is not one standard type of world. People sometimes talk about rocky planets as if they are all variations on Earth. Venus shows that is not true. Change the atmosphere, remove the oceans, and the whole surface starts evolving under different rules. The same category, rocky planet, can produce completely different landscapes depending on heat, pressure, chemistry, and internal activity. And that brings us back to the main question of the whole video, because the surface is not just there to look dramatic. It may hold the evidence for what actually happened to Venus. If Venus once had water, some minerals may still preserve signs of that interaction, especially if future missions can identify surface composition in much more detail. If Venus underwent enormous volcanic resurfacing, that process may have played a direct role in pushing the climate past recovery, by releasing greenhouse gases or by changing the crust in ways that weakened long-term climate regulation. And if the resurfacing was more gradual, then that tells a different story, one where Venus may have dried out over a long period instead of collapsing in one major episode. So the rocks are not background detail, they are evidence. They may tell us whether Venus dried out slowly, whether it was overwhelmed by volcanism, whether it had an ancient habitable phase that lasted much longer than expected, or whether the most important clues have already been buried under younger terrain. That is why mapping Venus better matters so much. Every lava plain, every rift, every volcano, every deformed highland could be part of the missing record of how an Earth-sized planet lost control of its own surface environment. And once you see that, the next question becomes unavoidable. If Venus and Earth were so similar in size and ingredients, and if Venus stayed geologically active while Earth stayed habitable, then why did Earth survive this process while Venus did not? What did Earth keep that Venus lost? Because that is where the story stops being only about Venus and starts turning directly back toward us. So why did Earth make it, while Venus did not? That is really the central question now. Because by this point, the difference cannot be explained by size. It cannot be explained by basic composition alone either. These are two very similar rocky planets, formed in the same solar system, from broadly similar materials, and yet one stayed habitable and the other became permanently hostile. So the answer has to be in the systems that regulate a planet over time. The slow, deep mechanisms that either keep a world stable or let it slide out of control. The first big difference is the carbon cycle. Earth has a long-term climate stabilizer that Venus may never have had in the same way, or may have lost very early. On Earth, rainwater interacts with rocks. Carbon dioxide in the atmosphere gets dissolved, reacts chemically, and over long periods ends up locked into minerals and sediments. Then plate tectonics helps recycle that carbon through the crust and mantle over millions of years. Volcanism puts carbon dioxide back into the air. Weathering and oceans help pull it back out. And over deep time, that gives Earth something like a thermostat. Not a perfect one, not a fast one, but a real stabilizing system. And that matters more than people usually realize. A planet does not stay habitable just because it starts out in a good place. It stays habitable if it has ways to correct climate drift. Earth warms, cools and shifts over time, but it also has systems that fight against extremes. On Venus, that full Earth-style loop seems to be missing. Without stable oceans, without long-term rainfall-driven weathering at the surface, and without clear evidence for Earth-like plate tectonics operating today, Venus may not have had a durable way to pull carbon dioxide back out of the atmosphere once it started building up. So while Earth could correct some long-term climate shifts, Venus may have had no real reset button. That leads directly to the next issue, plate tectonics. Earth's crust is broken into moving plates. Those plates collide, separate, sink, rise, and move heat and material between the surface and the planet's interior. That process helps release internal heat. It also helps cycle carbon and other chemicals through the crust, oceans, atmosphere, and mantle. It is one of the deep reasons Earth is such an active and self-adjusting planet over geologic time. Venus seems to work very differently. Instead of full-plate tectonics like Earth, many researchers think Venus may have a stagnant lid, meaning the outer crust behaves more like one broad shell rather than a set of moving plates. Others suggest Venus may go through episodic tectonic behavior, with long quiet periods interrupted by more dramatic overturn or resurfacing events. Either way, it does not seem to be doing what Earth does now. And that may be one of the most important differences between the two planets. Because if the interior and the surface are not exchanging heat and carbon in the same way, then two planets of the same size can still end up with completely different surface conditions. One can regulate itself over long periods. The other can trap heat, accumulate gases, and drift toward instability. So when people ask why Venus failed and Earth did not, one possible answer is that Earth had a more effective planetary plumbing system. Venus may have had the same raw materials, but not the same way of cycling them. Now add another layer to that: atmospheric loss. Earth has a strong global magnetic field generated by its internal dynamo. Venus does not have a comparable intrinsic magnetic field today. That difference is not the whole story, and scientists do not treat magnetic shielding like some magic force field that automatically saves a planet. But it does matter, especially when water starts getting high into the atmosphere. Once water vapor reaches upper layers and gets broken apart by sunlight, hydrogen can escape to space. A weak magnetic shield can make that process easier under the pressure of the solar wind and upper atmospheric interactions. So the missing magnetic field probably did not destroy Venus by itself, but combined with stronger solar input, atmospheric chemistry, and water loss from the upper atmosphere, it likely made Venus more vulnerable. In other words, once Venus started moving in the wrong direction, the lack of a strong magnetic shield may have made it harder to stop the damage. Earth had more protection in that area. Venus had less. And then there is one of the strangest differences of all: rotation. Venus rotates extremely slowly, and it rotates in the opposite direction from most planets, a retrograde rotation. That sounds like a weird side detail, but it may actually matter for climate. Some climate models suggest that slow rotation can sometimes help a planet by allowing thick, bright cloud decks to build up on the day side. Those clouds can reflect sunlight and reduce surface heating. That is one reason some simulations allow Venus-like planets to stay temperate for a surprisingly long time under certain conditions. But that just makes the story more interesting, because it means some features of Venus may actually have helped delay disaster instead of causing it directly. Its slow rotation may have created cloud feedbacks that bought the planet time, but apparently, if those effects were real and strong, they were not enough to save Venus permanently, or they only worked under limited conditions. So Venus may have had some temporary stabilizing advantages and still lost. That is an important point because it shows that planetary habitability is not decided by one single factor. It is not just distance from the sun. It is not just atmosphere. It is not just water, tectonics, or magnetic shielding. It is the interaction of all of them. A world can have one or two helpful features and still fail if the larger system does not stay balanced. And a world can survive not because it is lucky in one way, but because multiple stabilizing systems keep supporting each other over huge spans of time. So the clearest answer here is that Earth and Venus may have started with similar raw materials, but small differences added up. Venus got more solar energy. It may have had a harder time keeping water. Without long-lived water, the carbon cycle weakened. Without an Earth-like tectonic system, heat and carbon may have built up differently. Without a strong intrinsic magnetic field, atmospheric escape may have been more damaging. And once those problems started reinforcing each other, Venus drifted into a state that Earth avoided. That is the real message of this comparison. Size alone does not protect a planet. Being rocky does not protect it. Even starting with similar ingredients does not guarantee a similar future. Two planets can begin as close siblings and still end as complete opposites. Earth became a world of oceans, weather, and life. Venus became a world of rock, acid clouds, and crushing heat. And once you understand that, the next question becomes even more important. because now you want to know exactly when Venus lost the fight. Did it fail early, almost from the beginning, or did it stay stable for a long time before everything collapsed? Because the timeline changes the meaning of the whole story. The hardest part of the Venus story is not knowing what happened in the end. We know the end. The hardest part is knowing when it all went wrong. Did Venus lose its chance at habitability almost immediately, or did it stay stable for a very long time and then collapse later? That one timeline question changes the entire meaning of the planet. Because if Venus failed early, then Earth-like conditions may be easy to lose. But if Venus stayed temperate for billions of years, then an apparently stable world can still fall apart much later. Start at the beginning. Venus formed about 4.5 billion years ago, in the same violent era as Earth. This was the early solar system, when planets were still assembling, impacts were common, internal heat was extreme, and the surfaces of young rocky worlds were nothing like what we see today. Venus likely went through heavy bombardment, large-scale volcanic outgassing, and probably a magma ocean phase, maybe partial, maybe global, where huge parts of the surface were molten. So in its earliest stage, Venus may not have looked Earth-like at all. It may have been a brutally hot young planet covered in lava, steam, and thick gases released from the interior. That part is not especially controversial. Young rocky planets are violent places. The real question begins after that. Once the earliest chaos started to calm down, what happened next? Did Venus cool enough for liquid water to exist on the surface? Did it enter a more temperate phase? Or was it already too hot, too early, for surface water to stay stable? That is where the timeline becomes uncertain, and where the story gets much more interesting. Some climate studies suggest Venus may have had a genuine temperate phase, under certain assumptions about its early atmosphere, topography, and cloud behaviour. Some models allow liquid water to remain on the surface for hundreds of millions of years, and in some cases much longer, even up to billions of years. That is one of the most important possibilities in planetary science, because it means Venus may not have simply missed habitability by a narrow margin. It may actually have had it, then lost it later. And that changes everything, because there is a huge difference between a planet that was never really habitable and a planet that was habitable for a very long time before it failed. In the first version, Venus is a warning about how narrow the safe zone may be. In the second version, Venus is a warning about how unstable long-term habitability can be, even on a planet that seems to have made it. That is why this question matters so much. It is not just about Venus. It changes how scientists think about rocky planets everywhere. But it is important to stay honest here. That long-lived temperate Venus scenario is plausible, not proven. The evidence is still indirect. We do not have a clean rock record from ancient Venus the way geologists can study ancient Earth rocks. We do not have old coastlines photographed from orbit. We do not have drilled cores from the crust. What we have are atmospheric clues, surface clues, and models. Some of those models say long-term habitability on Venus is possible under the right conditions. Other studies push back and suggest the planet may have dried out much earlier. So if there was a temperate phase, what ended it? One major idea is the moist greenhouse transition. This is the stage where a planet gets warm enough that more water vapour reaches the upper atmosphere. Once that happens, sunlight can split water molecules apart more efficiently. Hydrogen escapes to space. And because hydrogen is the part of water that is easiest to lose, the planet starts draining its water inventory much faster. It is still not the full runaway greenhouse at first, but it is the beginning of a dangerous shift, because the water cycle is no longer staying close to the surface where it can help regulate climate. This is the turning point in the timeline. A moist greenhouse is where Venus may have stopped being a difficult planet and started becoming a planet that could not recover. As more water was lost, one of the main systems that could buffer climate started breaking down. Less water means less weathering, less carbon removal, and weaker long-term stabilization. More greenhouse gases stay in the air, more heat stays trapped, more water is lost. And once enough of the inventory was gone, Venus could have tipped into the stronger runaway greenhouse state that defines the planet today. So in simple terms, the sequence may have looked something like this. First, a violent young Venus, then possibly a cooler, wetter phase, maybe short, maybe long. Then a moist greenhouse transition, where the upper atmosphere became wet enough for rapid water loss. Then continued heating, continued carbon buildup, and eventual entry into the full runaway greenhouse state. That is the broad arc scientists are trying to test. The problem is that the exact timing of each step is still uncertain. Then there is another major event in the story, resurfacing. At some point, Venus's visible surface seems to have been extensively renewed. Scientists still debate whether this happened as a near-global catastrophic resurfacing event, where much of the crust was reset over a relatively short period, or whether it happened through more spread-out long-term volcanism and tectonic activity. But by the time Venus reached the state we see today, the planet had clearly become dominated by carbon dioxide, sulfuric acid clouds, and extreme surface heat. And that is important because the late part of the story is much clearer than the early part. We know modern Venus is the endpoint of major atmospheric and geologic divergence. We know it lost most of its water. We know the climate system now sits in a deeply hostile state. We know the surface has been heavily shaped by volcanism and tectonic processes. What we do not yet know is whether the most important transition happened early and fast or late and slow. That uncertainty is not a weakness in the science. It is exactly why Venus is still such a live topic. This is not a finished mystery. Scientists are still trying to reconstruct the missing biography of a planet. Every clue matters. The deuterium to hydrogen ratio matters. Noble gases matter. Surface mineralogy matters. Crater counts matter. Volcanic activity matters. The chemistry of the deep atmosphere matters. Each one is part of the same investigation, trying to answer not just what Venus is now, but when it became this way. And that is what keeps the tension high in this story. Because the timeline does not just tell you when Venus changed, it tells you what kind of planet Venus once was. If the transition happened early, then Venus may have been in danger almost from the start. If it happened late, then Venus may have stayed much more Earth-like for far longer than most people would expect. Those are two very different planets hidden inside the same world. So the best way to think about Venus now is not as a solved case, but as an unfinished reconstruction. Scientists know the final state. They are still trying to place the turning points. And the next question follows naturally from that. If Venus may once have had water, and may once have had a more temperate surface, then did it ever go far enough to support life? Even simple life? Before everything changed. So did Venus ever go far enough to support life? That is where this story gets much more serious, because once you start talking about ancient water and possible long-term habitability, the next question is unavoidable. If Venus once had liquid water on the surface for a meaningful amount of time, then in principle it may also have had conditions that simple life could tolerate. That does not mean life was there. Scientists are very careful about that distinction. Habitable does not mean inhabited. But if ancient Venus had the basic combination people look for on early Earth, liquid water, chemical building blocks and energy sources, then it moves from being just a failed Earth-like planet to being a possible lost biosphere candidate. And that matters because the threshold for simple life is not the same as the threshold for forests, animals, or anything complex. You do not need modern Earth conditions to make a world biologically interesting. Early microbial life can survive in harsh environments, and on Earth it appeared relatively early in planetary history. So if Venus had a long-lived temperate phase, even if it was only good for microbes and only for part of its history, then it may have crossed into the range where biology becomes a real question, not just a fantasy. But this is exactly where the evidence runs out. There is no confirmed sign of past life on Venus, no fossil record, no biosignature locked into clearly dated rocks, no direct detection of ancient biology. So the honest answer is that Venus may once have been habitable in principle, but nobody can currently say that it was inhabited. Still, that possibility changes how you think about the planet. It is one thing to say Venus became unlivable. It is another to say it may have become unlivable after once having a real chance. Now compare that with Venus today, because the contrast is extreme. The modern surface of Venus is far beyond the known limits of life. Temperatures are around 462 degrees Celsius, or 864 degrees Fahrenheit. That is not just hot in a normal sense. That is hotter than most kitchen ovens can reach, and it stays that way all the time. Then add the crushing pressure, about 92 times Earth sea level pressure, and a chemically harsh environment on top of that. Under those conditions, modern surface biology is effectively implausible under anything like known biochemistry. That is why scientists do not treat the surface of Venus as a realistic place for present-day life. It is not just one environmental factor that is too extreme. It is the combination. Heat alone is devastating. Pressure alone is severe. Chemistry alone is difficult. Put them together, and you get a world where even heavily engineered machines survive only for a short time. So when people ask whether life could exist on Venus today, the surface is almost certainly not where that story goes. That leads to the next question people often hear about: the clouds. High up in Venus's atmosphere, there are layers where temperatures and pressures are much milder than they are at the surface. And because of that, some researchers have periodically asked whether microbial life could survive in those cloud layers. On paper, that sounds less crazy than life on the surface. The environment at some altitudes is much more moderate in terms of temperature and pressure. So that idea keeps coming back. But once you look more closely, the cloud life case gets much weaker. The clouds are highly acidic, mainly made of sulfuric acid droplets. Water activity appears to be very low, which is a serious problem for life as we understand it. And the actual evidence for biology there is not convincing. The phosphine controversy is the best example. For a while, it pushed Venus back into the public spotlight, because phosphine was proposed as a possible sign of life or unusual chemistry. But the claim was heavily debated, the observations were reanalyzed, and it did not establish life on Venus. At most, it reopened interest in the planet and reminded everyone that Venus still has unresolved chemistry. So for this story, the cloud life debate is interesting, but it should stay in the background. It is not the strongest part of the case. The stronger and more defensible story is ancient habitability, not modern aerial microbes. The real scientific weight is in the idea that Venus may once have had conditions where simple life could in principle emerge or survive, then later lost those conditions completely. And that is exactly why Venus matters so much to astrobiology. Mars is often framed as the world that lost warmth, lost atmosphere, and became too cold and too dry. Venus may represent the opposite path. Instead of freezing out, it may have burned out. Instead of losing habitability by cooling down, it may have lost it by overheating and drying out. Those two planets sit on either side of Earth like two failed outcomes. One may have started with more clement conditions and then froze into a thin air desert. The other may have started with more clement conditions and then became a high-pressure furnace. That comparison makes Earth look much less inevitable. It suggests that a habitable planet may sit between multiple failure modes. A world can lose its chance by becoming too cold, too dry, too geologically inactive, or by becoming too hot, too greenhouse-driven, and too chemically extreme. Venus expands the definition of planetary death. It shows that a planet does not have to become cold and barren to become biologically unreachable. It can also become too hot and too dry for life to keep a foothold. So the strongest version of this section is not to claim that Venus definitely had life. We cannot say that. The stronger version is this: Venus may once have been a world where life was possible, at least in a basic microbial sense. And now it is a place where even spacecraft struggle to last for long. That contrast is enough. It gives the story real force without overstating the science. Because once you see Venus that way, not just as a permanently hellish planet, but as a planet that may once have been far more biologically promising, the whole thing becomes more disturbing. It means the planet next door may not simply be a failed world, it may be a lost one. And that makes the next question even more important. Because if this is the story scientists are trying to reconstruct, how do they actually know any of it? What missions gave us these clues, and what new missions are going back to finish the investigation? So how do scientists know any of this if Venus hides its surface under clouds and destroys spacecraft so quickly? That is what makes this part of the story so important. A lot of what we know about Venus came from missions that had to fight the planet every step of the way. Venus is not easy to study. It is bright in the sky, but it hides its surface under thick cloud. And when you try to go down into that atmosphere, the heat and pressure start destroying your hardware fast. So every good Venus mission matters a lot, because each one pulled information out of a planet that does not give it up easily. The first major breakthrough came from the Soviet Venera missions. These were some of the boldest planetary missions ever attempted. Several Venera probes reached the surface, and some of them sent back direct data and even images before failing in the extreme conditions. NASA's Venus Overview notes that 10 Soviet Venera probes made it to the surface. A few functioned briefly after landing, and the longest survivor lasted about 2 hours. Those short survival times are not a side detail, they are part of the evidence. Venus destroys spacecraft quickly because the surface is under extreme heat and pressure. The Venera landers proved that directly. They showed that Venus was not just cloudy and mysterious, it was brutally hostile at ground level. Then came the mission that changed how scientists saw the entire planet, NASA's Magellan orbiter. Because visible light could not see through the clouds, Magellan used radar to map Venus from orbit. During its first mapping cycle, it imaged more than 80% of the surface at far better resolution than earlier data. And over the full mission, it transformed Venus from a mostly hidden world into a geologically detailed planet, with volcanoes, lava plains, tectonic structures, and deformed terrain. This was the turning point. Before Magellan, a lot of Venus was still inference. After Magellan, scientists could start reading the surface as a real geological record. And Magellan is still paying off decades later. Reanalysis of its radar data found strong evidence that at least one vent near Mont Mons changed shape during 1991 in a way consistent with an eruption. And later, NASA reported evidence for eruptions at additional volcanoes in the early 1990s as well. That means Magellan did not just reveal an ancient volcanic planet. It gave scientists evidence that Venus may still be volcanically active now. That is a huge upgrade in the story, because it means the planet may still be changing in real time. Then Europe added another major piece with Venus Express. ESA's spacecraft arrived at Venus on April 11, 2006, and spent more than 8 years studying the atmosphere before the mission ended in 2014. Venus Express focused on atmospheric circulation, chemistry, cloud behavior, and escape processes. That mattered because by then, one of the biggest questions was no longer just what the surface looked like. It was how the atmosphere behaves now, and what that atmosphere can still tell us about lost water and long-term climate evolution. Venus Express helped strengthen the idea that the modern atmosphere still carries clues about hydrogen escape, cloud dynamics, and the processes that turned Venus into the planet we see today. And now the most important part. This story is not over. There is a new generation of Venus missions coming specifically to answer the questions behind this video. NASA's DAVINCI mission is designed to send a probe down through the atmosphere to study its chemistry, including noble gases and clues related to past water, and NASA currently lists its launch as tentative for 2030. NASA's VERITAS mission is planned to orbit Venus and map the surface and interior in much greater detail, with NASA listing launch no earlier than 2031. ESA's EnVision mission is also in development, with ESA listing a planned launch in November 2031 and backup opportunities after that. These missions are not being sent because Venus is a dead topic from the past. They are being sent because Venus is now one of the biggest open questions in planetary science. And look at what that means. Scientists are still trying to answer how much water Venus once had. They are still trying to figure out when that water was lost. They are still testing whether the surface is volcanically active now, how the interior works, and whether Earth and Venus were once much closer as climate cousins than they seem today. That is why the next missions matter so much. They are not just collecting more data, they are going after the missing parts of Venus's biography. So the real takeaway here is that everything in this story comes from hard-won evidence. Landers that survived for minutes, orbiters that used radar to see through clouds, atmospheric missions that tracked chemistry and escape, and now a new wave of spacecraft built to answer the exact question that still hangs over Venus. Not just what Venus is now, but what happened to it, in my opinion. And that brings us to the final step. Because after all the clues, all the missions, and all the competing explanations, you can now ask for one clear answer. What happened to Venus in the biggest possible sense? And why should anyone on Earth care? So after everything we have covered, what is the biggest answer? What actually happened to Venus? The simplest version is this. Venus probably started with many of the same ingredients as Earth. It was a rocky planet of almost the same size. It likely had a thick early atmosphere, and it may have had much more water than it has now. But because Venus was closer to the Sun, it was under much stronger solar heating from the start. Over time, that likely pushed the planet toward a moist greenhouse, and then a runaway greenhouse state. Water was lost, long-term climate regulation weakened, carbon dioxide built up, and Venus turned into the hot, dry, high-pressure planet we see now, with sulfuric acid clouds above, and possibly active volcanism still shaping it today. But the longer scientific answer is more important, because Venus was probably not changed by one single event. It was likely a chain reaction. Venus received more solar energy than Earth. Its early atmosphere evolved under hotter conditions. Water in the upper atmosphere was broken apart by sunlight, and hydrogen escaped to space. As water was lost, one of the planet's biggest stabilizers disappeared. Without long-lived oceans, and without an Earth-like long-term carbon cycle, volcanic carbon dioxide may have accumulated more easily. If plate tectonics was limited or absent in the Earth-like sense, then Venus had even fewer ways to bury carbon and regulate climate over deep time. So this was probably a system failure, not a single cause. One lost stabilizer made the next loss harder to stop. Water loss weakened climate control. Greenhouse gases built up. The atmosphere thickened. The surface overheated. And eventually Venus became locked into a hostile state. And even now, one of the biggest questions is still unresolved. Was Venus only briefly Earth-like, or was it Earth-like for a very long time? That difference matters a lot. If Venus stayed habitable for billions of years before collapsing, then stable climates on rocky planets may be more common than we thought, but also more fragile. If Venus only had a short window of habitability, then Earth-like conditions may be rarer and easier to lose early. That uncertainty is not a weakness in the story. It is one of the strongest parts of it, because it means Venus is still an active scientific mystery. That is exactly why new missions like DAVINCI, VERITAS, and EnVision are being built, to figure out how much water Venus had when it lost it, and how the planet's surface, interior, and atmosphere evolved together. And this is why people should care. Venus is not just a strange planet next door. It is one of the clearest tests of what keeps a rocky world stable and what destroys that stability. It helps scientists understand the climate tipping points, ocean loss, atmospheric escape, and the difference between a planet that stays habitable and one that does not. It also changes how we look at exoplanets. A distant planet can be Earth-sized, rocky, and in a roughly promising orbit, and still be much closer to Venus than to Earth. So Venus is not just a lesson about the past of one planet. It is a warning about how easy it may be to misread a world from far away. And the strongest way to end this is not just to say Venus is hellish. People already know that. The stronger ending is this. Venus may be what Earth could have become under different conditions. Two planets with nearly the same size. Two rocky worlds born in the same system. One kept its oceans. One lost them. One stayed within the range where life could survive. One crossed a threshold and never came back. And that is why Venus matters so much. It is not just another planet. It is the closest example we have of how a world that starts with familiar ingredients can end in total climate ruin. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video